Welcome to section 3.5, using linear inequalities in one variable to make predictions. So the inequality parts are our little alligator signs, so things like less than, greater than, less than or equal to, greater than or equal to. So we're comparing one quantity to another quantity, and when it's a linear inequality, so we know what a linear equation looks like, so I'll just make up something like 3x plus 2y equals 12. So that's an equation, there's an equal sign. Now that it's an inequality, we can take the same thing and now replace the equal sign with the less than sign. So this is in two variables. The one we're doing, that's actually going to be later on in 3.6, but essentially when it's an inequality, we're going to be working just like equations, but using an inequality sign, one of our four inequality signs. Okay, so we're going to be interested in solutions to our linear inequalities. So we're going to solve inequalities by isolating the variable, much as before. So we're going to have to go over our properties. The first one is the addition property of inequality. And to illustrate this, let's start off with something like 3 less than 5. Okay? And then what we're going to try out is we're going to take 3 less than 5, and we're going to add a number to both sides, and we're going to see if it's the same. So for instance, let's add positive 2. And when I say the same, I mean, does our inequality still work? So if we add the same number to both sides, is 5 still less than 7? Yes. Okay, and that's for a positive number. Let's try the same thing but with a negative number. So still 3 less than 5. And now we're going to add a negative number. Adding a negative number is like subtraction. All right, so does the inequality still hold? So is 1 less than 3? Yes, that's a true statement. So for any number C, if A is less than B, then A plus C is less than B plus C. So this is just saying we're allowed to add or subtract the same number to both sides, and the inequality still holds. And I just happen to do less than, but we can use any of our inequalities. We can use less than, greater than, less than or equal to, etc., etc. All right, let's do the same thing with our multiplication property. We'll bring back our example 3 less than 5. And now we're going to be multiplying both sides of our inequality by the same number, and we're going to see if our inequality holds true. So let's multiply both sides by positive 2. All right, so does our inequality still hold? Is 6 less than 10? Yes. All right, good. So that's looking good. Let's see with the negative number, just like we did with subtraction. So we'll start with 3 less than 5, and now we'll multiply both sides by the same negative number. We'll just do negative 2. Keep the tradition alive. Okay, so we want to know if our inequality still holds. So does negative 6, is that less than negative 10? All right, so remember the alligator eats the bigger number, and negative 10 is actually smaller, right? It's sometimes handy for negative numbers to draw out a real number line. All right, so negative 10 is less than negative 6 because it's to the left of negative 6. That's how numbers work, right? Just like negative 6 is less than 0 because it's to the left. Negative 10 is to the left. All right, so does this inequality hold true? The answer is no. So in order to make it true, we can make it true really simply. We can just switch the inequality sign. We can write -6 is greater than -10. And then that solves our problem. So when we're dealing with multiplication, so the multiplication property of inequalities, if C is a positive number, then if A is less than B, then, I'm going to switch over. We'll say AC is less than BC. Sorry about that. And then for a negative number C, if A is less than B, we have to flip the inequality. For that reason we just showed, right? Because in that previous example, C was negative, C was less than 0, so you have to flip the inequality. All right. Those are our two properties we're going to use to find solutions. So on to our next page, find solutions to linear inequalities by isolating the variable using the above properties. And again, that's just like linear equations. Okay, so again, it's a similar strategy. We're going to isolate the variable just like linear equations. And an example would just be something like this, where we have one variable x, and all of the exponents on the x are 1. So this is a linear inequality. And I like to know, as far as my strategy goes, when you're solving equations, the variable can go on the left or right. But I like to keep the variable. You don't have to do this. I like to keep the variable on the left. It's easier for me to read the inequality that way. Then I don't get confused. Okay, so let's look at this first example. So we're going to solve 2x plus 1 less than 9. And note that before you even solve it, there are several solutions. There are several numbers that are actually less than 9. So if you can make 2x plus 1 less than that 9, then you are a solution. For instance, I can plug in, if I plug in 0, I'm left with 1 less than 9. I can plug in 1 because 3 is less than 9. If you plug in x equals 2, you get a true statement, right? I can plug in some ridiculous numbers like -100. That would be, let's see, -200 plus 1 is -199. That's less than 9, right? So we have all of these different solutions. And at some point we stop, like if we were to plug in 4, 4 wouldn't be a solution because that would be 9 less than 9. And 9 isn't less than 9, right? 9 is equal to 9. So let's find all the solutions. Now that we kind of get that there's infinitely many. And we do this by isolating the variable. So just like with our linear equations, we move the constants to one side, the right side. And once we have variables on the left and constants on the right, we divide by the coefficient. We have to be careful here. We have to make sure it's not negative. And here we're dividing by +2. So everything stays the same. And then we get our solution as x less than 4. All right? And then this would be an inequality. So it turns out any number less than 4 is going to make 2x plus 1 less than 9. And remember, we're not including the 4 because we don't have that equal sign. If we had that equal sign, then 4 would come to the party. But we're strictly less than. So this means numbers like 0, 1, 2, 3, -100, and then something less than 4, we could even add in 3.999. because 3.999 is less than 4. But you should make a note that x is not allowed to be 4. That's not part of our solution because we're just strictly less than. Okay, so when we're communicating our solution, so less than 4, we're going to be able to do it in 4 different ways. What we have right here, x less than 4, is an inequality. That's one way to state your solution. You can also use a graph. So if you wanted to use a graph, we could draw, I'll just do it right here, a real number line. And we'll say 4 is right here. And x less than 4, so all numbers less than 4, are we going to the left or to the right of 4? We're going to the left. So you can do something like this. It says all numbers to the left. And to show that we're not including the 4, that our solution set does not have 4, you can do one of two things. Some textbooks do an open circle like that. And then our textbook does an open parentheses. Okay? We're also going to be learning about interval notation. So let's start looking at all of those. So first of all, let's see. In words, inequality graph, interval notation, we write it, it almost looks like an ordered pair, but it's not an ordered pair. It's something that tells us where our interval starts, comma, and where our interval ends. Okay, that's our interval notation. So let's start with some inequalities. Let's start with x less than 2. Then we'll write x less than or equal to 2. X greater than 2. X greater than or equal to 2. Okay, so at the top, x less than 2. In words, that means all numbers smaller than 2. And it doesn't include the 2. The graph for that is a real number line. We're not including the 2, so we'll do a parentheses. And now it's the same as before, x less than 2. So we're going to go to the left and do a parentheses right there. Okay, so now interval notation. So again, our interval notation, it has a starting point and an ending point, and we read left to right. So if we look at our graph, this arrow means it goes on forever. So if we're reading left to right, it starts at, well, let's see, like negative 100 would be included, negative 1,000, negative 1,000,000. In other words, we're going all the way to negative infinity. So the starting point, we're going to start at negative infinity. And then we end at the 2. All right? So again, 2 is not included, but like 1.999999999 will be included. So we're going to write 2. And then to communicate that we're not going to actually put 2 in our solution, we're going to do a soft parentheses, just like with our graph. And infinity is not a real number, so we're also going to do a parentheses on infinity. Okay, let's see what happens when we include 2. So first of all, our graph, when we include 2, so now x is less than or equal to 2. We're still going to the left of 2. Now we're going to do a bracket like this. And that means include the 2. And then as far as the interval notation goes, we're still starting at negative infinity. We're still ending at the 2. But to communicate that it's included, now we're going to do that hard bracket, just like our graph. So everything is the same. The graph and the interval notation are very similar. All right, and then in words, we can say something like all numbers less than or equal to 2. So 2 is in the solution set. All right, and then let's see how greater than 2 changes. Everything, still really similar. All right, so we are going to be starting at 2, and x is greater than 2. So what direction are we going this time? To the right. Numbers to the right are bigger. And again, draw it up into the 2, and then do that soft parentheses on the 2. So for our interval notation, we start at 2, and now we're going off to the right forever. And so that's infinity. And again, infinity always has parentheses. All right, and then in words greater than 2, we can say all numbers bigger than 2. All right, so like 2.0001 is in there, but 2 is not included. When you get to the greater than or equal to 2, that's all numbers bigger than or equal to 2. All right, and then the thing that changes on our graph this time is we have a bracket on the 2. That's telling us to include the 2, and then we're going to the right. All right, so our interval notation mimics that graph. All right, so we have a bracket, 2, infinity. Okay, so let's go ahead and solve some more problems. And we're going to state our answer using an inequality and interval notation. Okay, so like I said, I like to keep the variables on the right. So to isolate the b, you gather the b terms on the left, constants on the right. So we have to do 2 things. Move that 3 over by addition, and then move that 7b over by subtraction. I'll do everything at the same time. So now we have negative 5b is greater than 25. Okay, and then let's divide out by that coefficient. And when we're dividing out, what do we notice we're dividing by? A negative 5. So since we're dividing by negative 5, greater than has to flip to less than. Okay, and so then it's b is less than, and that's the only thing we change. So 25 divided by negative 5, we still do the normal quotient. The only thing that changes is the sign. We still divide the same, we still divide by negative 5. Okay, so b is less than negative 5. So it's all numbers smaller than negative 5. So we're going to start at negative infinity and go up to negative 5. Are we including the negative 5? No, we're not. So we have a soft parentheses. Let's look at another example. So we're asked to solve. I would push pause right now and solve it yourself, and then push play. All right, so isolating that variable, we're adding a 1. And now that we have constants on one side, variables on the other, now we divide. And I want to say a common mistake is to flip the inequality, because notice it's negative 15 divided by 3. But the inequality stays the same, because the 3 that we're dividing by is positive. And our rule is only flip it when we divide by a negative number. So our denominator is positive, we leave the inequality. All right, so that's our inequality notation. If we wanted to do our interval notation, all numbers smaller than negative 5, that means we're going to negative infinity, going up to negative 5. Are we including the negative 5? Yes, we are, because it's less than or equal to. Moving right along, here's a more complicated example. So just like before, same strategy with our linear equations. You clear the parentheses first, gather your like terms. So please push pause, see if you can solve it yourself, then come back for the solution. Let's distribute the -3 there. So negative 6x minus 3. And then we'll distribute the -2. Okay. Gather like terms, -6 minus 2 is -8x. Minus 3 minus 8. Whoops. Do you guys see my mistake? It's not an equal sign. It's greater than or equal. Okay, so the variable's already on the left. Let's add 11 to both sides. Get the variable on the right. And then divide by -8. And so your solution is x. What do we do with the inequality? We have to flip it because we divided by -8. All right, everything else stays the same. Okay, we're getting a lot of less thans, so we're still off at -infinity. And you guys are including that endpoint. Okay, final example of this. Think back to your strategies for equations. If you have fractions in your linear equations or any type of equation, you can multiply through by the LCD to clear the fractions. And you can do the same thing with inequalities because we're allowed to multiply the same positive number to both sides and nothing changes. All right, so with that strategy in mind, go ahead and push pause, then come back. Let's see how we do. Okay, so multiplying the equation, let's see, what's the LCD? I'm going to go, I can always do multiples of 8, so 8 to 16 to 24. 24 is a number that 8, 6, and 3 divide into. So I'm going to multiply 24 to each term after we distribute. So I can do that intermediate step. Some of you guys might be able to cancel as you go. And if you can, that's fine by me. So this first term, 24 divided by 8 is 3. 5 times 3 is 15. Here we're left with the 4b. And then 24 divided by 3 is 8. 2 times 8 is 16. And we can always slow that process down too. Okay, so after all this manipulating, now we can finally start solving our inequality. Let's put our 15 on the other side. Whoops. Sorry, this is 2 times 8 is 16. There it is. Let's go back and check to make sure I didn't do any other mistake. Okay, subtract that 15 from both sides. And we get that b is greater than 1/4. Okay, so I'll write interval notation up here. So all numbers bigger than 1/4, so we're starting at 1/4, and now we're going off to positive infinity. All right, infinity always has a parentheses. And are we including the 1/4? No, we're not. So it gets a parentheses. There you go. And in general, if it's bigger than, if our solution set is b is bigger than a number, and positive infinity will be the ending point. If it's b less than a number, as in before, negative infinity will be your starting point. Okay, so negative infinity is always the starting point, not allowed to be here. And positive infinity can only be an end point, can't be right here. Okay, so moving on. We're going to 3-part inequalities. So an example of this, and we've used them in describing domains and everything. So that's just an inequality. A three-part inequality is adding another part to that, right? So literally 3 parts, 2 inequality signs. And again, we read left to right, so normally the numbers are smaller on the left-hand side, and then this is telling us it gets bigger, this is telling us it gets bigger. So remember, the alligator eats the bigger number. And then visually, if we wanted to see this, okay, we're looking at something like this, and we're going -6 to 10, all right? So we're moving, again, left to right. We can use a bracket for our solution set. I also wanted to mention that in other textbooks, sometimes other than a bracket, they'll do a solid dot. So we can do something like that. Okay, so here is this 3-part inequality to solve. And we have to keep everything balanced. So whatever we do to one part, we have to do to all parts. And our strategy, our solution is going to look something like this that we just wrote. So we're going to isolate x in the middle. We're going to isolate x in the middle. Okay, so we're going to put all of the x's in the middle and then all of the constants not in the middle. So if we're isolating the x, we'd have to add 5 first. And then that would cancel out that -5. But whatever we do to one part, we have to do to all parts. We have to do it 3 times. So we're looking at -10 less than or equal to 2x less than 7 plus 5. All right? And then to isolate the x, we're going to come through, we're going to divide out by the coefficient, and 2 divided by 2 is 1. So that's perfect. We'll just have x. But whatever we do to one part, we do to all parts. So we're going to do it 3 times. And now we're looking at -5 less than or equal to x less than 6. And then now we can write our interval notation. So you can make a graph if that's helpful to you. So always make a graph if that's helpful. We're starting at -5 and we're ending at 6. And remember, we're not including 6 in our solution. So we're going to have this soft parentheses. And then our interval notation is going to be really similar to our graph on the real number line. So that's our solution using interval notation. I wanted to mention in this next example, let's say we took this step right here, and rather than a 2x, we did a -2x. I wanted to show you how that would change our answer. So what do we know about inequalities and dividing by negative numbers? Well, all of our inequalities are going to be flipped. So the less than or equal to's are going to become greater than or equal to. And then the division of is the same. -10 divided by -2 is +5. 12 divided by -2 is -6. And there you go. And notice our inequalities, normally when we're doing a 3-part inequality, it's getting bigger. So going left to right, the alligator is eating the number on the right. This is backwards. So if it's more helpful, write it smallest to biggest. And it's just sometimes a little bit easier to see that way. And then remember, here the alligator is eating the x. It's turning away from the 6. And then that next one, the alligator is eating the 5, turning away from the x. So everything's consistent. And now we have that same format, or the traditional format of our 3-part inequalities. And there you go. Okay, let's move on to some word problems. So we have that the percentage of residents of Ohio who smoke was 20.3% in 2009 and has decreased by about 0.85 percentage point per year since then. The percentage of residents of Wisconsin who smoke was 18.8% in 2009 and has decreased by about 0.61 percentage points. Predict in which years the percentage of residents of Ohio who smoke will be less than the percentage of residents of Wisconsin who smoke. Okay, so let's see how we're going to go about this. So, Ohio smokers, I'll write it in words, and Wisconsin smokers. And we want to know when the percentage of residents of Ohio who smoke will be less than the percentage of residents of Wisconsin who smoke. Okay, so let's make a model. So we have to model the percentage of residents of Ohio who smoke. And we know that it was 20.3% in 2009, and has decreased by about 0.85 percentage points per year. Okay, so if we say that T is years from 2009, this would be your y-intercept, like we've seen in Chapter 2. And this would be your rate of change. So we could look at something like that. There's the rate of change. T is, and remember to make it negative since we're decreasing. And there's your y-intercept. All right. And then same thing with the Wisconsin smokers. The residents that smoked, it was 18.8% in 2009, so that's your y-intercept, and we decreased by 0.61 per year. So that's your rate of change, and we're decreasing, so it's negative. And there's your y-intercept, the percentage in 2009. So now we're going to solve our inequality by moving our variables to the left, our constants to the right. We get negative 0.24 is less than negative 1.5, and so we're going to divide out by that 0.24, negative 0.24. So because we're dividing by a negative number, we're going to flip the inequality. All right, so we're going to get T is greater than 6.25. So this is saying after 6.25 years, the residents of Ohio who smoke, the percentage will be less than the percent of the residents of Wisconsin. So that's going to happen in year 6 after 2009. So our solution, we could just say after the year 2009 plus 6 is 2015. And there you go. Let's look at something similar, another word problem. So one U-Haul office rents 10-foot trucks for a one-day fee of $19.95 plus 0.6 or 69 cents per mile. One Penske office charges a one-day fee of $29.95 plus 39 cents a mile. We're going to let U of D be U-Haul's charge and P of D be Penske's charge for driving D miles in one day. All right, so U of D, we have a flat rate of $19.95, and then for every mile D, it's $0.69, 69 cents. So that 0.69 is your rate of change for every mile. So if you drive 2 miles, it'll be 0.69 times 2. If you drive 5 miles, it's going to be an additional 0.69 cents times 5. And then you have that flat fee, $19.95. And then P of D, the flat rate is $29.95, and now the rate of change is 39 cents per mile. Okay, and we want to know for how many miles driven is the one-day charge at U-Haul less than the charge at Penske. So when is U of D After how many miles is it less than P of D? All right, so U of D, here we go. All right, there's this for U of D, and then P of D is this. And now let's solve our equation. Excuse me, let's solve our inequality. So let's move our variables to the left. Constants on the right. And let's see what we have. You have 0.3D less than, let's see, that's just 10. And so if we drive less than 10 divided by 0.3, or if we're driving less than 33 1/3 miles, then the one-day charge U-Haul is going to be less than the charge at Penske. So for how many miles driven, we could say 33 less than 33.3 miles. Then U-Haul will be a better deal. And then after that, U-Haul will be a better deal. And then if it's bigger than that, like if you're driving 34 miles, then Penske will have a bigger deal. And you can even check that by, if we were to plug in 4 for D, 0.69 times 4 is 276, plus that flat rate is 2271. But then Penske, when D equals 4, if you guys have your little calculator, it's 3151. So there you go. Okay, so let's enhance our understanding. Okay, so for this, you guys have all the information you need. It's kind of a review of before and just kind of exploring what it means to be inequality. I'm not going to walk you through it. You guys are going to do it yourself. So go ahead and push pause. And then when you push play, I'll have the solution written out for you. All right, and here's maybe some kind of solution, some idea of what it really means to be less than a number.